This is an energetics question. There's calculations in here, but there's also a 6 marker, and that 6 marker is based on the energetics required practical. So try each section. When you've gone through the whole question, carry on through the rest of the video to review. Here's part A, part B, part C, and we'll now look at part A. So we've got here some data. We need to work out which of the two reagents is in excess, and then once we've done that, we can work out the enthalpy of reaction. So I've been given a concentration and a volume of zinc sulfate, and I've been given a mass of magnesium. Let's start with the zinc sulfate. If I have a concentration and volume, I can work out the number of moles. You'll note here that I've converted my 50 cm cubed to decimeters cubed because my concentration is in moles per decimeter cubed. I'm then going to take my magnesium. I've been given the fact I have 2.08 grams. My atomic mass is 24.3, so that allows me to work out a molar quantity there. I've now got 2 of the 6 marks for some very straightforward calculations. The magnesium is in excess, doesn't get a mark on its own, but that's quite important for what we're about to move on to, because we're now going to do an energetics question. We're going to use Q is mc delta T. There's a big clue there that we've been given the specific heat capacity, which will always be provided. That's 4.18 for C. If I put those figures in and showing you there where they have come from, we can calculate Q. Now, the temperature is the temperature change. So that 37.3 has come from the 61.2, take away 23.9. My mass is the mass of surroundings. That's the mass of solution the reaction's taking place in, which is water, and we will always assume a density of 1. From there, I can work out Q, and that's in joules. But that doesn't take us to the end of the question. I don't want joules, I want kilojoules per mole. So the first thing, I need to convert it to kilojoules, and then I divide it by the number of moles. And you'll notice I've used zinc sulfate. That's because that's the limiting reagent. It's the one that's not in excess. I put all of that together, and I get to an enthalpy of reaction of negative 156 kilojoules per mole. Moving on to part B, we have another student using the same method obtaining a value for the enthalpy of reaction of negative 142. But that's a big difference from the databook value of negative 310. What's the most likely reason? Well, it's a very short answer actually, despite the space given. It's heat loss. If heat is lost, we don't get a true measure of the energy change within the reaction. And that's really what the 6 marker is leading to. The 6 marker is asking you how you can take the method that we've used so far and improve it. But the good news is this is a required practical that you are improving it to. So I'm going to add the criteria, whether you're level 3, level 2 or level 1. As always, if you cover all 3 stages effectively, it takes you into level 3. If you cover 2 stages effectively or 3 stages partially, you get to level 2. And level 1, if you cover 1 stage very well, or you've covered 2 stages to an acceptable degree. Now let's take a look at the 3 stages that we need here. The first one, we can improve the insulation, and calorimetry is generally done in a polystyrene cup, often with a lid. And question B was really guiding you towards this. It prevents that heat loss. That's not the only thing that's different. I'm hoping that when you think calorimetry, you can remember a specific graph that you would plot to work out the maximum temperature rise. Now, the first part of that is that you would improve the temperature recording by recording the temperature for 3 minutes, maybe, before you add the metal. That's going to allow you to establish an accurate start temperature. Is the room temperature stable? Is it going up? Is it going down? And then the final improvement is we carry on measuring the temperature after the reaction has taken place, and we plot the results every minute. That allows us to generate a cooling curve that we can extrapolate back to the point that the metal was added and the reaction began. And the purpose of that is that we can identify a theoretical maximum temperature rise had the reaction happened instantaneously without any heat loss.